from a physical interpretation standpoint, to keep with our recognition that ionization of scandium involves loss of these electrons before you touch this. In this case, MPD can be said to be more important than penetration. Here's the most important penetration region for the 4s electron, where it's very close to the nucleus. And on being very close to the nucleus, will experience a considerable degree of nuclear attraction, as opposed to the degree of nuclear attraction which the electron feels when it's out here. But ionization takes away the 4s electron, so here the penetration region does not dictate the electron lost on ionization, because 3D remains until the 4s electrons are gone away. Now, question 23A, a simple question. The question in the notes say, which atom in the periodic system has got the shortest 1s orbital radius? I changed it to read, which atom in the periodic system has the shortest 3D orbital radius? I'll give you a hint. The answer to this is the same as the answer to the question as it's stated in the notes. Which atom's got the shortest 1s orbital radius? Which atom in the periodic system is going to exert the strongest attraction on 1s electrons? You won't find the answer looking at this chart. Look at the periodic table in the notes, up near the front of the book. I'll give you another clue. As things stand, we do not know the name for this atom. But you see its atomic number. What is it? 118. The most proton-rich atom is always going to exert the strongest attraction on 1s electrons. So which atom in the periodic system is going to have the shortest 3D orbital radius? Which atom in the periodic system is going to have the shortest orbital radius for any kind of orbital? The one with the most protons in the nucleus. Provided, you got to be careful about this, what I just said. Let me think about this before I say it. No, I think we're all right with what we said. I'll leave it stand and I'll think about it some more. I don't think there's a problem with that statement. Now, on pages 23, 13, and 14, some review stuff. Because I'm sure you all heard about rationalization of ion sizes in Chemistry 2045. Two types of ions: cations, positive ions, anions, negative ions. What happens to the size of an atom like sodium when you remove from it an electron and create a positive charge? The resulting ion has got to be smaller than the parent atom. And in a case like sodium becoming sodium ion, you expect that this electron loss is going to result in a substantial shrinkage in size. Think that's a fair conclusion? Because the valence electron for sodium is in energy level number 3, isn't it? And when that electron is lost, you don't any longer have any energy level number 3 electrons. And creating a sodium ion, which is isoelectronic with neon. Now, in the resulting cation, clearly you have smaller electron-electron repulsion than what you had in the parent atom because you got one fewer electrons. You also have a proton-to-electron ratio which is now greater than 1 to 1. So the average nuclear attraction experienced by each remaining electron is greater than it was for the parent atom. Opposite effects set in when to an atom you add an electron and create an anion, like the fluorine atom becoming the fluoride ion. Now, the electrons will experience greater repulsion among and between themselves because you got more electrons in the electron cloud, and a smaller degree of average nuclear attraction because now the proton to electron ratio is smaller than 1 to 1. So, upshot, atom becomes a cation, shrink. And if the electron lost in making the atom a cation accounts for removing all the electrons from the highest lying energy level, big shrink.
I thought because of superposition principle that the proton to electron ratio wouldn't matter. Is that not true?
I know not of what you speak. Where did you hear this?
Physics, just I'm thinking of field theory.
I know not of this. Now, one more comment. Please bear in mind that the size considerations which I apply to ions involves treating the ions as if they are isolated gas phase particles. You will see data which will suggest to you that the sodium ion is larger than the neon atom. But these data are reflecting the size of the sodium ion when it is observed as part of a crystal lattice that contains sodium cations. And when an ion is in a lattice, its size is affected by the surrounding particles. And the immediately surrounding particles in a stable lattice will be anions. That's not what I'm talking about. Because as I said, if you look at a data table where ion sizes are reported as a consequence of observing sizes and doing some calculations from ions as part of a crystal lattice, they're not isolated. My contention is the Na plus particle has got to be smaller than the neon atom if you treat the Na plus particle as an isolated gas phase species. Why do you think I say that? Do you recognize Na plus and neon are isoelectronic? They have exactly the same electron configuration. But what's the difference? Na plus has got 11 protons pulling on that configuration, and Ne has got 10. So from a simple Coulombic standpoint, I argue that if you treat an ion as an isolated gas phase particle, then Na plus has got to be recognized as being smaller than Ne. Something we can talk about, but something we can't do. Because we can't get these cations and anions as isolated gas phase particles and measure their size. So, we can talk about it, which I am, but we can't do it. Now, Please, on page 2314, take a look at the statement that you see in bold font in the middle of the page. In order to provide us, in a simple way, to line up monatomic particles, anions, cations, atoms. In order to line these particles up in order of relative size, the statement in bold says, if I consider all the atoms from a given period and monatomic ions derived from these atoms, any atom will be larger than any cation. Period number 3, sodium, magnesium on down through argon. Sodium ion, I now argue, on the basis of this statement, to be smaller than any atom from period number 3. And based on size trends, which atom in period number 3 do we expect to be smallest? Argon. And as far as argon is concerned, that's about the end of this consideration, because practically speaking, argon doesn't show us any chemistry. On the other hand, or to extend this statement, it also says that any negative ion, any anion I create from an atom in a given period will be larger than any atom in the period. Because in general, when I add an electron to an atom and create an anion, I will observe or expect to observe a rather substantial increase in size. Can there be exceptions to what I just said? You betcha. But if we're going to try to line up monatomic species, cations, anions, and atoms, in size order, we'll abide by this directive. Now, I've already said, atomic size is really a can of worms. I don't know that I used this term before. Ionic size is a can of worms. I can't get a hold of these isolated gas phase ions and observe their size. And getting the actual size of atoms in many cases is very difficult. Because when you get atoms in contact with each other, they affect each other's size, especially if they make bonds. An example. This circle represents a sphere, a nitrogen atom sphere. This egg-shaped thing represents a nitrogen molecule. What happens to the size of a nitrogen atom when it meets with another nitrogen atom and they get together to make a nitrogen molecule? Is the size of the N atom in the N2 molecule bigger or smaller than the size of the isolated, free, unbound N atom? Do you think that an assured driving force underlying bond formation, do you believe that atoms do make bonds in nature? Do you think the carbon and oxygen and hydrogen atoms, which are connected with each other in this wood, are rather strongly bound to each other? I already asked you the question, do you think iron atoms are strongly bound to each other in a sample of iron? If you don't think so, go get an iron hammer and conk yourself in the head with it. See which gives way. The iron hammer head or your head? But if you're going to do that experiment, let me know first so I can talk to my lawyer I don't want my students to accuse me of having instructed them to do an experiment which caused them to have, at the minimum, a severe headache. They want to blame it on me. So it leads to more of this difficulty in assessing the size of these particles. Clearly, when atoms bind with each other, the principal driving force is that the valence electrons, when the atoms make the bonds, the valence electrons, which get associated with each other to make the bonds, the valence electrons get more stable on bond formation or less stable. What do you think? Why in the hell would they bond with each other, these atoms, if the electrons got less stable? That wouldn't make any sense, would it? Now let's look at the nitrogen molecule. I don't believe as yet we've spoken of the term covalent radius. This is a measure of the size of an atom which is in the bound state. I've seen textbooks which seem to interchange these terms, and that's confusing. I use atomic radius as a reference to the size of an isolated atom all by itself. Covalent radius is a measure of the size of the atom which is in the bound state. The nitrogen atom in the N2 molecule is going to be a lot smaller than a free nitrogen atom all by itself. Because these valence electrons, which dictate the size of a nitrogen atom, get much more stable when they interact with another nitrogen atom and make this molecule. Well, now, if I can get a hold of a nitrogen molecule, and this I can do, what would you do to measure the size or report to me the covalent radius for a nitrogen atom in the bound state? What would you do? I want a measure of the size of the nitrogen atom in the nitrogen molecule. A measure of the size of the nitrogen covalent radius for the N2 molecule. Well, you measure this bond length. That we can do. Observe the positions of the nucleus of each nitrogen atom. Take the bond length and divide it in two. And this distance is the covalent radius of the nitrogen atom in the N2 molecule. Does that fix the size for an N atom in the bound state? Unfortunately, no. Because this side of the N atom and the electron density on this side of the N atom is not shared electron density. This electron density isn't going to be as stable as this electron density. So, if I observe the size of the nitrogen atom in the N2 molecule at a position in space which is directed away from the bond, I'm going to get a van der Waals radius. Did you hear about van der Waals radius in 2045? Now we got atomic radius and covalent radius and van der Waals radius. How big is this damn thing? Well, let's have more fun. Let's go to the hydrazine molecule. I've taken the liberty of writing a Lewis picture here, left off that non-bonding pair. I want to get a handle on the size of the nitrogen atom in the hydrazine molecule. Well, as soon as I measure bond length and strength for this thing, I see that I got a longer bond and a weaker bond. This is a single bond between N atoms. Here's a triple bond. Well, how big is the N atom in this molecule? Well, I'll observe the position of this nitrogen nucleus, and I'll take this bond length and divide it in two, and I'll play this game. And I now got a longer covalent radius. I mean, this doesn't surprise me from a chemist's perspective, because this thing is got nitrogen-nitrogen single bond. Here I got nitrogen-nitrogen triple bond. But I still got a problem. What if I observe the size of a nitrogen atom in this molecule and I want to get it by taking a look at the HN bond? Well, here's the hydrogen nucleus. And these bound atoms. Here's H, here's N, and you really have an electron density distribution that's rather like this. And here's another electron density distribution like this, and another electron density distribution like this. Because when the H atom and the N atom meet with each other to make a bond, their electron clouds overlap. So where the hell in this bond, where do I draw the line? Where do I say, okay, that's the end of the H atom electron cloud and the start of the N atom electron cloud? Can I do that? No. So this is a can of worms. Trying to decide on the size of an atom is really a very confusing issue. For the free atom, fine, if you can get a hold of it. But as soon as you start talking about bond formation, then this size thing is puzzling, to say the least. Here's calcium versus bromine ion. Calcium atom, bromide ion. Which is larger? Well, let's look at the periodic table. Calcium and bromine atoms are both from period number 4. Size comparison of the atoms, no problem. The size trend demands that we realize that bromine atom is a lot smaller than calcium atom. Okay so far? But when I add this electron to the bromine atom, I observe a considerable expansion in cloud size. The bromide ion is a lot bigger than the bromine atom from which the bromide ion was derived. What counts more? I don't know. And I can't get an isolated bromide ion to observe the size, the actual size of an isolated bromide ion. I don't know. Puzzling, isn't it? In any case, what we are interested in, which I've already reminded you about, is to be able to look at atom sizes more or less on a relative basis in order to support our ability to establish rationale for Bronsted-Lowry acids and bases and their strengths. Pardon me, not and their strengths, but their strengths. But a couple more questions on this stuff, and then we'll jump into the stuff we're really interested in, chapter 23, the acid-base stuff. Question 23.9, as it follows from these funny pictures we've looked at, these radial probability graphs. Scandium. Lose an electron, becomes scandium plus. Lose an electron, becomes scandium double plus. Lose an electron, becomes scandium triple plus. Based on radial probability, where do you expect to see the largest size gap? Now we know every time you lose an electron, you're going to see shrink. But based on radial probability, where would you expect to see the largest shrink, the biggest size gap? Between these two? Between these two? Or between these two? Well, really, I've provided you with the information that you need with our previous peek at the scandium electron configuration in conjunction with this funny picture right here. When this becomes this, I lose a 4s electron. Right? But I still have a 4s electron. So the remaining 4s electron will dictate the size of the scandium plus particle. But when this becomes this, does this have any remaining 4s electrons? Does this have any remaining energy level number 4 electrons at all? This now just has energy level number 3 electrons. Now if I were to take this graph D, which is an overlay of the 4s radial probability function on the 3D probability function for a particular atom. And I want to put on this picture the radial probability function for 3s. Where would MPD for 3s be relative to what we got on the board? Take a look at radial probability graph C. Based on what we've said, we would expect the MPD value for 3s to be somewhat to the right of the MPD value for 3D. Now, additional studies on this stuff, experimental as well as theoretical, show that for multi-electron atoms like transition metal atoms, which have 3D and 4s valence electrons, the 3D and 3s, 3D and 3s MPDs are damn near indistinguishable. But we'll stick with our conclusion that the highest n value s electrons dictate the size of species. That may not be true, but I'm making that statement because it at least keeps with the radial probability functions which we have so far examined. Unfortunately, the radial probability functions which we have so far examined are for hydrogen-like species. A very great simplification of the actual case. So, at the minimum we realize, when we go from scandium plus to scandium double plus, no more energy level number 4 electrons, no more 4s electrons. Well then, does this look like a pretty big size shrink? Yeah. Now, when we go to scandium triple plus, here to convert this to this, we finally lose this 3D electron. Scandium triple plus is isoelectronic with argon, the nearest neighbor noble gas of scandium atom. Based on what we have said, what electrons are responsible for determining the size of scandium triple plus? Let's back up a moment. What electrons are responsible for determining the size on the basis of what we said? What electrons are responsible for determining the size of this thing? Scandium double plus. Is it 3D1? Because that's still there for this. Based on what we have said, what electrons are responsible for determining the size of scandium double plus? What? (3s). Aren't they there? They're very stable. Because now penetration dominates MPD. Once we strip away the 4s electrons from scandium by these successive ionization processes, we now have 3s electrons, as it follows from what we've said, dictating the size of this species. All right? 2310. Do it. Look at the species whose formulas are listed in the notes to help you get started. For the species listed for question 2310, all these monatomic species, some ions, some atoms, line them up in order with respect to relative size, smallest to largest. Which is the smallest species? Look at the formulas. Tell me the smallest species, the formula for the smallest species listed in regard to question 2310. What is it? I got to vote for Li3+. Anybody second that vote? Do you realize that Li3+ is a bare nucleus? You bet that's the smallest species. All the rest of them got electrons. Largest? Look at the formulas. Tell me the formula that you see, which you believe is the formula for the largest of the listed species. What is it?
SB3.
What's the name for SB?
Antimony.
Antimony. That's correct. There's one other triple minus species listed in this, contained in this list. It's a phosphide ion, P3 minus, but phosphorus and antimony, they're in the same family, aren't they? But SB is 2 periods down. SB's got a whole bunch of valence electrons, a whole bunch of high n-value electrons that phosphorus doesn't have. Question 2311. How would you line these 3 species up with respect to relative size on the basis of what we've said? Which of these is smallest? Give me the formula. That's isoelectronic with neon, isn't it? That's smaller than A+. If I treat these species as isolated gas phase particles. All right, then we have Na and Mg+. What can you say about Na and Mg+? They're isoelectronic, aren't they? They have identical valence electron configurations. So with that, I state that the only factor which can determine a difference in size between these species is what? Protons. For Mg+, you got 12 protons pulling on this configuration, and only 11 for Na. So for these 3 species, smallest, largest. 2312. One more size question. Hydride ion. Hydride ion is derived from the hydrogen atom by popping 1 electron into H, which converts H into H minus, the hydride ion. Lithium, the first atom of period number 2, and the largest atom in period number 2, right? How do you expect the size of Li, the atom, to compare to H minus? Do you think H gets a lot bigger when you give it an electron and turn it into H minus? If you think about it, you will realize that no known species has a smaller proton to electron ratio than H minus. 1 proton, 2 electrons. You really have reduced nuclear attraction when you go from H to H minus. And we learn from our considerations about helium that 2 electrons in the same orbital do shield each other. So not only do you have the case of one proton pulling on two electrons, you now have two electrons shielding each other as well as repelling each other. Do you bet H minus, if you could see H minus next to H, you bet H minus would look like a basketball next to a ping pong ball? I would. H minus has got to be a hell of a lot bigger than H. What a small proton to electron ratio. And a considerable degree of electron-electron repulsion. Only two electrons. There's only one proton attracting these species. So how does H minus compare size-wise to lithium, given that H minus has only got energy level number 1 electrons? The answer is, I don't know. How can I tell? And interestingly enough, when we get to this level of analysis, in this case for size of species, the most common right answer is I don't know. I don't know. You think this H minus thing is a good reducer? Well, I've provided some information here. H minus becomes, oops, 1/2 H2. If H minus becomes 1/2 H2, E0, is it plus 1.13 volts or minus 1.13 volts? What do you bet? We're thinking about putting this in our half reaction table. I won't, because you can't get H minus as an isolated particle. But do you think this E0 value is plus 1.13 volts or minus 1.13 volts? Based on what we said about H minus, big size expansion when you put an electron into the H atom. A lot of electron-electron repulsion. Weak proton to electron attraction. Do you think H minus is pretty stable? You're going to find out when you go, for example, to organic class, for those of you who go there, hydrides. Hydride compounds are commonly used as potent reducers. Potent reducers. They're also marvelous bases. You think H minus would have a naturally strong attraction for H plus? If H minus grabs H plus, it becomes this. If H minus loses an electron, it becomes this. Is this a plus or minus sign? What do you think? You betcha. This is a damn good reducer. And now, finally, we get started with the stuff we're principally interested in. 2317 and 2318. Electronegativity. A brief review. What I find, and I believe I've already told you this, is that students have all heard about electronegativity in Chemistry 2045, but few of them have an idea of what it means. If I asked every one of you right now to write a working definition of electronegativity, what would you write down? A working definition of electronegativity. I'll provide you with this. A measure of the ability of a bound atom, a covalently bound atom, to attract and stabilize valence electron density. A measure of the ability of a covalently bound atom to attract and stabilize valence electron density. It's in the notes. Electronegativity trends. I already told you, I told my students when I talk about this. FON. It's a lot of fun to think about electronegativity. FON. Fluorine number 1, oxygen number 2, nitrogen number 3. Although nitrogen and chlorine are practically tied. But there's a hell of a lot more materials which are of great importance containing nitrogen in their composition relative to those which contain chlorine in their composition. Do you believe me that amino acids are important? Proteins, are they important? Arguably, I think more important than sodium chloride. Even though you might like that on your hamburger. Now, the first consideration we are going to make in regard to laying foundation for developing an ability to rationalize Bronsted-Lowry acid strengths, base strengths as well, is that of orbital electronegativity. EN, I'm just adding an O in front for orbital. Orbital electronegativity. These two species. Write the Lewis picture right now on your paper for this thing. You don't have to write the Lewis picture for this thing because we got it over here. I covered it up. I'll uncover it. Here it is. If I observe the size of a nitrogen atom in this molecule, I will get a nitrogen atom size, which is a covalent radius, which is smaller nitrogen atom size for this species, but larger nitrogen atom size for this species, and much larger than the free nitrogen atom. Isn't that nice? I'm talking about nitrogen, I already got 4 different sizes. Question. We know this is a shorter bond and a stronger bond because of the double bond. Could we provide an argument based on orbital electronegativity? Now let's lay foundation for understanding this orbital electronegativity. We already have in what we talked about earlier. Let's do it again. You are an electron. You're moving into energy level number 3. And you observe vacancy sign in front of 3s, 3p, and 3d sublevels. They're all empty. You can move in any one of these orbitals. You, the electron, Mr. or Ms. Electron, as the case might be. In which of these orbitals do you take residence? 3s, 3p, or 3d? 3s, because that's where you're the most stable. So tell me, which of these orbitals, sublevels, which of these sublevel types, 3s, 3p, 3d, has the highest orbital electronegativity? Which one? 3s. That's where the electrons are stabilized to the greatest extent. Now, let's expand that to hybridized orbitals. You learned about hybrid orbitals. In energy level number 3, do you realize how many hybrid orbital types we can create? From energy level number 3, where you've got 3s, 3p, and 3d orbitals. You can create sp, sp2, sp3, sp3d, sp3d2. Do we have to stop here? Hell no. sp3d3, sp3d4, and let's grind them all up. sp3d5. There you are. Now I know in 2045 you didn't talk about sp3d3, But if you had a central atom with 7 peripheral atoms bound to it, you need a hybrid that's a composite of 7 orbitals. If you had a central atom with 8 peripheral atoms bound to it, you need sp3d4. And 9 peripheral atoms, you need sp3d5. This is just a game we play. Orbitals aren't real. These are all energy level number 3 hybrids. Which one of these has the highest orbital electronegativity? Which one of these has the lowest orbital electronegativity? From a hybrid standpoint, if all these hybrids were empty, and you were an electron and going to move into one of these, which one of these would you move into? You're going to move into one where you're going to be most stable. In which of these would you be most stable? You bet the answer to the question has got to be extremes? Well, more stable here or more stable here? Which one? You realize this thing is 50% S character? Making orbitals is like making sausage in the butcher shop. You grind up an S orbital with a P orbital. You grind up a pound of pork and a pound of beef. You turn the crank and you get out 2 pounds of sausage. 50% S character, 50% P character, 50% beef character, 50% pork character. It's not pure beef or pure pork anymore, like an SP hybrid. 50% S character, 50% P character. This thing is only 1/9 S character. Well, if you're more stable in an S pure orbital, pure atomic orbital, then of hybrids you're going to be most stable in this hybrid because 50% S character. Now you apply what we just said to answer this question. Why, from an orbital electronegativity standpoint, is this bond shorter and stronger than this bond, but longer and weaker than this bond? And why is this a stronger Bronsted acid? Here's this acid-base stuff coming. Why is this stuff a stronger Bronsted acid than this stuff? And we'll pick it up from this point tomorrow. And I advise you strongly to read this stuff that we are now going to discuss in detail, because we're going to zip through this